Got it.
Okay. My name is Jason Dolenshai. Most of you have never met, so hi. First of all, thank you to Greg for inviting me to speak. My first Burlington Data Science meetup was a month ago, so I came and kind of checked it out. Now I'm giving it a shot, so we'll see how it goes. Feel free to ask questions at any time. There's a handful of slides. This is meant to give you a very broad overview to the field of reinforcement learning, which is quite a large field. And then there is some code at the end to sort of demonstrate some of these concepts in practice. By the way, can you do me a favor? Raise your hand if your primary language is Python. Okay. Raise your hand if you've used bandit algorithms or reinforcement learning in the past. Excellent. And if you've used a Bayesian model. Yes. Okay, perfect. That just helps me for pacing. So
Someone's raising their hand.
oh yeah.
Can you unmute yourself, Quentin? I think.
They were just we all raised our
Oh, I see. Sorry.
Yeah, we were just playing along. Sorry.
That's signaling. So here's a quick outline. Yeah, there is a thing for that. Yeah. No sweat. A quick intro. A look at what real-life RL systems look like. Some examples of applications. Some concepts and formalism. Just to sort of set the stage. The most interesting part really is the demo. So let's see if I can get there quickly. Ask questions as they come up. So here's how the stage is typically set. Let me dash this. I can get rid of it. Oh, there you go. Right. So have you ever faced a decision where you had to choose between relying on what you know or trying something new? It's sort of a strategic dilemma. Imagine you're a gambler facing a row of slot machines. This is like the classical scenario. You want to maximize your long-term winnings, but each machine produces an unknown reward. So what do you do? Yeah, what do you do? Yes, well, you can use computers and data. This situation is frequently called a multi-arm bandit problem. If you've ever done anything with bandits, you've probably seen this picture before. It's like the only bandit picture. You have K options or arms, they're frequently called, to choose from. And in each trial, you have to decide whether to maximize expected reward or to give up some expected reward to gain new information, effectively buying information. The only way to maximize your long-term gains is through balance. So this is a pretty simple diagram, but a very clear picture of how reinforcement learning systems work. Reinforcement learning is a framework for machine learning. It's not an algorithm per se. It's a little bit more like cross-validation than like regression, if you like. You can use it in conjunction with many kinds of machine learning approaches. And it is useful for optimizing decisions that are made over a sequence of repeated trials. And it generally looks like this. There's an agent, that's like the model. And there's an environment, that's the stochastic environment. This could be like an e-commerce digital sales channel where data is being generated. This could be feedback from, say, the road and the visual surroundings if you're in an autonomous driving kind of application or flying application. There's lots and lots of examples. We'll talk about a little bit more of those. At every time t, the environment reveals a state to the agent. The agent has to choose an action based on that state. The environment then reveals a reward as a consequence of the action. The agent takes the reward, updates its beliefs, and then the next trial comes along. That's all it is really. So unlike traditional supervised learning, reinforcement learning is unique in that there's no historical training step necessarily. You should do that, and it can help, and we'll talk about that. But in general, you switch the thing on and it starts making predictions, and updating and evaluating come next. So it learns by interacting with its environment directly, as opposed to having historical training data that it trains on and then makes predictions after the training set, right? So as I said, an agent interacts with this environment through a sequence of repeated trials. And the agent maximizes long-term reward by managing a trade-off between exploitation and exploration. All of you, I think, are probably familiar with another famous trade-off between bias and variance. Most of machine learning is predicated on quantifying and navigating these trade-offs. This is quite like that, just slightly different. Exploits means to maximize expected reward, given what you know, and to explore means, like I said, to basically buy information, to sacrifice a little up front with the hope of gaining something down the road. I Googled clip art for try something new, and this came up. And my wife said, "Oh yeah, my sister's husband loves peanut butter burgers." So shows you what I know. This would be new for me, and maybe it's new, but there you go. I see some skeptical looks. Okay.
Trying to figure out what else besides peanut butters.
All right, look, maybe onion rings. I'm not sure I can do that. Editorial aside. Okay, the agent exploits when it uses data to select an action. So this is where it's really trying to maximize its expected reward. This can be done, for example, by making predictions with an ML model. A lightweight agent can make predictions using only a reward signal, like a 1D signal. And more complex agents can use other information as well. When there's a feature set powering the decision, you have something like a traditional classifier or regression model as the decision engine. This is called a contextual bandit. That's the area of extremely broad and active research. And there's lots of cool things you can do with contextual bandits in lots of different everyday problems. So we talked about balancing, explore, and exploits. We talked a little bit about exploits. The agent explores to gain new information, to avoid local optima, and to adapt to changes in its environment. One way to do this is getting specific to one implementation of a bandit model. One way to do this is to dedicate a fixed percentage of trials to decisions made uniformly at random. This is called epsilon greedy exploration. So fully greedy decisions are where you're always trying to maximize expected reward. Epsilon greedy means set aside epsilon % of those trials. Basically flip a coin, sample a uniform random number, and if it's less than some value epsilon, instead of using the data, you select one of these arms uniformly at random. So basically cover your eyes and throw it out. This is introducing heterogeneity into the decision-making process. You can probably tell from the description it's a pretty coarse way to do it, and there's lots of other ways to do it. But that's probably the first, the most famous example, epsilon greedy exploration. Another method for exploration, a more specific sort of application, involves managing this balance somewhat differently. Instead of using expected value and maximizing expected reward and then going, with uniform sampling for exploration, alternatively, this constructs and maintains information about the full rewards distribution and samples from that distribution. That is called Thompson sampling. And then we're going to look at how this works in practice. I think many of you are probably familiar with this. It's a Bayesian model of beta binomial model. We'll talk more about that. This picture here, these are just some pictures of beta distributions. The expectation is actually, there's two parameters in the distribution. The expectation is alpha over alpha plus beta, alpha beta being the two parameters. So you can see it's sort of like those vertical dotted lines. Those are the expectations. Obviously, that's collapsing the information available in the full distribution in every one of these cases. We'll explore a little bit more of that once we get to the Python. We're making pretty good time. Any questions? Great. So I touched on contextual bandits. That's really getting us up to the starting line for like where the actual stuff happens. This is part 2 of the starting line. It's really expensive and complicated to test everything you want to test exclusively in the online environment where things are happening. You're like serving prices to customers or making decisions or driving a car down the streets or what have you. So as a complement to gain a lot more efficiency and flexibility, you can set up offline optimization in order to try stuff out, see how it works, and then allow the offline results to inform the online tests. So in this way, you might do something like feature selection or learn some weights for a model. Decide here's what I want to try out, like in an A/B test against a holdout or against another reinforcement learning agent. In the online environment, see how that goes. This kind of loads the dice in your favor. Starting with offline optimization. Again, a broad area, and these two fields of research are kind of parallel to each other, contextual bandits and offline optimization. Just to ring the name bell, there's a guy called John Langford, who I think is really the pioneer of a lot of these methods. He uses Microsoft, I think, and Yahoo before that. It's when many of these papers were written, which is like the 2010s. They started to show up contextual bandits papers and offline optimization papers. And there's lots of stuff you can do with offline optimization as well. Maybe we'll have an opportunity to go a little deeper. So one really important characteristic of reinforcement learning, it's true that it learns by interacting, but perhaps even more consequential is the fact that suppose, like in this case, you have 3 arms in the bandit. At every trial, your agent is making a decision. So suppose like there's these 3 doors, I choose door number 3, that door opens and there's a goat. But for that trial, I don't know what would have happened if I opened door number 1 or door number 2. This is really important. These are called partial information. And this is like a gigantic differentiator between what constitutes a bandit problem and a supervised learning problem. In supervised learning, how did I write it here? All training set labels are fully revealed. That's exactly right. You know all the ones and all the zeros a priori. In reinforcement learning, you do not. There are ways, interestingly, any supervised learning data set can be used in a bandit problem. You do that by basically sampling and withholding the reward signal for those actions which are not chosen, etc. That's how offline optimization works, and we can talk, it's a little bit more complex. We can talk more about that. Partial information, really big deal, especially when you're doing contextual bandit stuff. Does it make sense why this is true? So here's just like a grab bag of applications. Some of the most famous big papers about this stuff were like in the, I think, 2010s, things like AlphaGo. DeepMind is training computers to like beat humans in playing Go, beat humans in playing StarCraft. Lots of applications in autonomous vehicles, in industrial settings, robotics certainly. My favorite examples that have really guided me much more closely are sort of in the B2C segment of technology. That's where I've done a lot of work. Netflix and Spotify have published quite a lot on their use of bandit algorithms as well as offline optimization to get better results from bandit algorithms, and even language models. Reinforcement learning is not the main event in training language models, but it is part of the equation, the so-called fine-tuning step, used as a technique called reinforcement learning with human feedback sometimes. Actually, there was a little blurb about it on the OpenAI blog post unveiling ChatGPT and saying we're using this stuff. It's really like sort of the cherry on top for LLMs. They're effectively supervised models. You can just sort of like give them additional information through this method to, again, fine-tune them. Okay, a quick rundown on vocab. The formalism and stuff, I mean, usually it's just a matter of vocabulary and not being afraid of notation. Same situation here. So a policy, and RL has like very specific language in some cases. The policy is a decision-making rule. You can sort of think of this as like the algorithm. This is what you want to optimize and use to make decisions. The context in the contextual bandit case is all of the information available to you at time t, let's say. The action is the output of the policy given the state or given the context. That's the decision that the bandit or agent makes. And the transition matrix just gives the probabilities for going from one state to another. Don't know too much about that. But basically, the big object that's up here is a Markov decision process. This is like the most formal setting for a bandit problem. To say when you have a Markov decision process, which is like a stochastic environment, stuff's happening, repeated trials, that's the setting for training a reinforcement learning agent like this. Assuming that it has, it obeys the Markov property, that's really important. That means the path independence is on your side. You don't have to keep track of everything that's ever happens in order to make the right decisions. And then stationarity, this is always something that shows up. Homogeneity in time, if the distributions that are generating the data or the empirical processes you're observing are changing all of the time, it's very difficult to get any traction with the model. Interestingly, when you start messing with this assumption, you can really see the value of reinforcement learning because in general, non-stationary environments are much more realistic. Things happen, external shocks happen. Reinforcement learning agents and the use of exploration allows your programmatic decisions to be a lot more robust to changes in the external environment. And that's exactly what we're going to see just in minutes. A couple of other important buzzwords. So regret, frequently instead of maximizing gains, these problems are characterized in terms of minimizing regret versus like an optimum policy. There is this sort of platonic ideal of the optimum policy where you get maximum rewards. And then your policy's regret is the reward stream coming from The optimum policy minus the reward stream coming from your own policy, right? It's just it's one minus the reward signal, effectively. And then value and control. So these are just ways to characterize the different pieces of the decision-making problem that you're trying to solve. Solving the value problem means forecasting expected reward. Solving the control problem means maximizing expected reward or making a decision based on the forecast. This is, again, just vocabulary basically to indicate how it's not so important to get choked up with the formulas and the notation. If you read the papers or you read the textbooks, there's a lot of math. Usually it's just vocab, and you can kind of skip it. So far, so good. Great. Again, just to touch on what you actually do when you're using these kinds of techniques, this is a very powerful and widely applicable family of techniques. There are numerous opportunities for optimization, including different explorer strategies. I mean, you mentioned a couple like Thompson sampling, epsilon greedy. In addition, you could imagine simple ones where the value of epsilon or the proportion of trials where you are exploring decreases over time as you accumulate information that would sort of have like a decay on it. Sometimes it's called epoch greedy. What else? The value of epsilon or the explorer decision could be made as a function of other variables. So there's an example where you have your machine learning model making a prediction with a confidence interval. And if it's high confidence, then you take that and use it. And if it's not that high confidence, you can explore instead. There's a version called, I think, adaptive greedy, which paper that shows that performs quite well. Different exploit strategies, that amounts to different supervised learning methods that you use for the exploit engine. And those can be, and that's arbitrary. That can be, depending on the reward, it could be a classification or regression. You can use neural nets or shallow methods, gradient boosting, etc. Contextual bandits, that's sort of like, just a regression problem or a classifier where you have a feature set going into the decision. And then reward shaping is really interesting. This is where, like, suppose that you are any kind of business, Spotify, for example, they've written papers about this. Their goal is not to optimize the value that they extract at every click, but rather to have high lifetime value customers, right? So the data that you can collect about lifetime value is very sparse if you're looking at the low bias signal. So instead, you introduce more and different kinds of information, proxy information into the reward signal, higher bias, lower variance. You get a little bit of a denser picture of what is contributing. Like basically, it would be drivers of high LTV predictions, right? If you have an LTV predictor model, you know which features are important. You can include those in the reward signal for something like this to sort of like embroider or more information into the reward signal. That's called reward shaping. All of these, in order to do these effectively, would really require you, it would be very difficult to do this without offline optimization, extremely slow and expensive. So setting up that offline simulation framework, which we're going to see a toy version of coming up next, is really, really critical.
What do you mean by offline optimization?
Yes, excellent question. So there's a little picture in here, not the world's best picture, but reinforcement learning that we're talking about. You have an agent, it's interacting with its environment, and over many trials, it's like learning to do something and trying to get better, right? But then suppose that agent is using like epsilon greedy exploration. And you say, that's okay, but it's kind of like, I want to try something a little slicker. One way that you could do that is to introduce another bandit into the online environment and run an A/B test, right? That's a very reasonable thing to do, but in order to gain a little bit more efficiency, instead of just launching a test with something whose results you don't know quite how to handicap yet, you could first try to do this test offline. What that amounts to is using either historical or synthetic data and some clever sampling in order to say, it's like a counterfactual move. If I had this thing running online against this data, here's how it would have performed. This just requires like some subtle sampling. This is really like John Langford's and co-authors' incredible Mozartian sampling contribution in his papers about contextual bandits. We'll talk about that more in a moment if you like. But basically, it's building a simulation using either synthetic data or historical data, where you have to really explicitly prevent bias from sneaking in. But in this way, you can basically bootstrap a bandit environment, a synthetic online environment, to say like, if I have bandit A and bandit B running against each other, A beats B, so that looks like a good candidate to test against B, the baseline, in an on test. And that's how offline optimization works, sort of, in a nutshell. Does that make sense? I'm glossing over a lot. Right. I will gloss a little bit less in just a moment. So on the right, just to get this thing out of the way, this is a picture of ostensibly a beta binomial model converging over time. You know how Bayesian models work in the distribution, which narrows as information accumulates, right? So suppose that we have a sequence of repeated trials with a binary reward signal, right? 0, 1. You can think of this as like coin tosses, conversion decisions, to make it a little bit more realistic, anything like that. Reinforcement learning is not limited to binary reward generating environments, but this is a simple. We can use a beta binomial model to estimate the win probability over a sequence of trials, right? So a cleaner way, if you forget about slot machines and forget about like e-commerce, a cleaner way to think about this from a probabilistic perspective is like, suppose that you have, in our case, we have k equals 3 in the code. So suppose you have 3 coins, and we're going to flip the coins a bunch of times and play this game, and the goal is to get as many heads as you can. Every time we flip the coins, you have to choose which coin you're going to go with, right? Basically, you're trying to learn the win probability, win head probabilities for each coin. So you can use beta binomial statistics in order to do this. We're going to look at doing this in the RL setting. In the RL context, this is called Thompson sampling. Why? Because before the Bayesian language and everything really existed in like 1930 something, this guy called Thompson wrote a really complicated paper about doing something like this. Hard to read, but that guy's called Thompson sampling. And with that, oh, by the way, here's some references and stuff. If anybody, so there are some bandit enthusiasts in the audience, I think we saw. There's a little bit of sacrilege going on here. Anybody who's done anything with reinforcement learning has heard about this book, the Sutton and Bartow textbook. It was like the first reinforcement learning. There's no sacrilege because I put it backwards, it's alphabetical. I was going to put the second book first because I think it's a better book. It's like more of a math book. You know, it's like reading the primary document versus something that's maybe 30 years newer. I find it a little bit more clear, a little bit more explicit. The original book, I mean, these guys are like discovering this new field and writing this textbook. You know, they started working on this stuff, I think, in the 60s. So it was all pretty primordial. Like if you read any, you know, old school 70s, 60s computer science papers versus reading something on the subject. Today, it's like a little bit easier to learn from the more recent sources sometimes. Of all places, the University of Alberta has a really active and really high-grade research program because of a couple of faculty members. Lots of high-grade research coming out of the University of Alberta in RL. And there's a million different blog posts and articles and tutorials, et cetera, that you can find all over the place. Some more technical than others, but there's plenty of resources. So now I'm going to make the jump over. This renders a little better in GitHub. Yeah. Cool. So there's a lot of information here. What is this thing going to do? This is like a toy version of what you might see in offline optimization. Basically, it's a simulation framework, in this case using synthetic data, that is effectively auditioning 2 different bandits against each other to understand which one performs better under what circumstances and why. In order to narrow the scope, this is about the simplest version of this thing that you could cook up. In order to narrow the scope, we're assuming a binary reward signal. And we're going to look at the difference in performance between greedy decisions that are made right here. I'll talk about this in a little bit more detail. But greedy decisions that are made by taking expected values, and alternatively, RL decisions that are made by sampling from the same distribution. So the greedy move here is to always treat the beta distribution by hitting it with an expected value. In every case, when you see a beta distribution, you automatically take it. The RL move is to maintain something beyond just the first order, first moment information, and say I have this whole distribution and I can generate random samples that incorporates a little bit more of the full variance. This is how exploration is finding its way into the decisions in this case. Okay, that's a preview. So I'll go back upstairs. Thompson sampling means using the beta binomial model in reinforcement learning. For those who, and I think everybody probably knows this, this is a Bayesian model for a binary reward signal that matches the binomial likelihood that matches with the beta prior. These things are all conjoined together and they play nice together. That's how conjugate priors work. The most important relationship is between the data and the likelihood function. Anytime, so forget about RL for a minute. Suppose you want to build a model and you want to use a Bayesian model. The thing that you do is to look at your target variable and look at, say, a histogram of that variable, and then you say, okay, this looks like, for example, it's counts, right? Then if you know Poisson distributions are usually used to model counts, you can set up a kind of model that way by matching the Poisson likelihood to that target variable. Or alternatively, this is real values, but restricted to the positive half of the real line and it exhibits some skew, or whatever. You look at the characteristics visually of the target distribution, use that to select a likelihood, use the likelihood usually through the conjugate prior. Or alternatively, sometimes you have more not closed form methods where you have to do more sampling, and that's where it gets more computationally intense. There's a lot to say about Bayesian models. This is the simplest Bayesian. The most important relationship between the data and the likelihood, that's how you figure out what model you're using. And that gets us as far as the imports. So there's nothing too crazy here. Stop me if there's something you want to talk about for the imports, globals. These globals run the simulation. Going to have many paths, many steps per path, many paths per epoch. An epoch is basically like a trip through the simulation. You do this a bunch of times in order to use, the law of large numbers in order to take averages and get more robust measurements. This is a very important variable. This is a 3-armed bandit problem. Those are the true win probabilities for the 3 arms, right? And one of the things that well, first let me say, this bandit stuff. Those are the win probabilities, right? That's important. And we'll come back to that. Here, there's 2 Python objects that are implementing bandit models using the exclusively greedy decision-making rule and the RL decision-making rule. You can see it uses inheritance to borrow characteristics between one and the next. I think that's probably something you've seen before. I usually steer clear of object-oriented programming, especially in Python, but it makes a lot of sense for something like this. Any questions about that? That's a question. Okay, now these 2 helper functions just do what they look like. That's very small. This is just because the notation is different. The NumPy API doesn't have a Bernoulli. It just says binomial 1p is Bernoulli. That's fine. And then policy here, this is just how we're going to make decisions in order to, again, make it more digestible. I just wrap those up there. This sim function is where the thing actually happens. Most of that, from output down, ignore that. That's just logging. This part here, you can also ignore. That's basically logging. This is super important. So one thing that is different in this simulation from what you would use in practice, or the example that this is taken from, which is not a very, it's not a work example. They just kind of mentioned this in a famous tutorial from Stanford on Thompson sampling. This adds a little bit of a curveball, again, in order to demonstrate how these things work in practice, and that is to introduce some non-stationarity into the environment. So we said that this is usually a big assumption. Stationary models are important. Stationary environments are important so that your model can learn something and then not be thrown off on the next trial. But in the real world, customer behavior can evolve. The stochastic environment that an autonomous vehicle is trying to ingest can evolve. Any of these sorts of scenarios, you have external shocks happening all the time. So if we can introduce something that simulates that into this simulation, then we can also measure and observe how RL adapts to those changes and how it handles this. These shocks, these external shocks, are implemented here by shuffling the win probabilities for the arms. So these arms, right now, they're initialized to look like this. Obviously, if you call this 0, 1, 2, arm number 2 is the winner by far, but every few trials, and we're going to see, it's pretty explicit, let's see, these get jumbled around. So the values are the same, they just get permuted, right? What does that mean? It means that a bandit that already knew that, say, arm number 2 was always going to win, on the next trial is now wrong and has to figure out what to do. So far, so good? So the sim function simulates a path through the dynamic environment, solves value and control problems, and outputs results. The simulation experiments varying degrees of non-stationarity. The results are then compared to measure the impacts on RL performance. Again, this gives an approximation of real world behavior. Critical implications of partial information. Like I described before in the 3-arm case, the true, quote unquote, true full reward signal is at every trial is a 3-element array, right? There are truly, like, again, 3 arms. There's really rewards for any choice that you make. But empirically, you can only make a single choice for a trial. So that reward is basically collapsed. Does this make sense? It's like one of the trickier bits. That's called partial information. Again, there's important practical consequences. We'll see what that amounts to. So one of the cool things about reinforcement learning is that you kind of have to think about machine learning inside out. It's not the case that you train and then predict and then evaluate, but rather you predict and then evaluate and then train, right? You switch the thing on, it starts going, and it's learning from like time 0, basically, online learning. So how does it work? This is the reward signal, they're Bernoulli, right? For P and probs, that's that vector of probabilities we saw, the true and probabilities. Predictions are made for the 2 bandit policies using the objects that we saw above. Actions are then selected by applying this policy function is again just the argmax. What is an argmax? It means find me the thing that generates the highest of whatever. So in this case, the predictions are estimated win probabilities. The argmax then would be the arm corresponding to the highest win probability. Yeah, because you want to select the arm that's going to maximize your long-term gains. That's what this guy does. Keep track of the actions. Now you evaluate by, this is where the partial info thing happens. All rewards, again, this has 3 elements, right, for P and props. But over here, the only one that's observed is the one corresponding to the action that's actually selected. This is like, if you like physics, and the physics person, wave function collapse, right? You're getting rid of the information that's not observed. Similarly for policy B, and then interestingly, the same thing is true for models. So if you only see one element of the reward signal, you're only eligible to update 1 model per trial. You have 3 models in this case that are making predictions in parallel, 3 models, 1 for each arm. You're only really permitted, not really, you're only permitted full stop to update one of these models per trial because you only observe a single dimension of the reward signal per trial. This is the tricky part. If you can wrap your head around that, then you're in the clear. Also, there's a little implementation detail here. You could easily imagine whether it's a Thompson sampler like this or a full-on contextual bandit like classifier. Suppose you have 5 arms, binary reward signal, contextual bandit. You can either have 5 parallel binary classifiers or a single integrated multi-class model. Whether you choose one or the other is essentially a matter of style. And I like the parallel binary classifiers because it's a little bit more functional and a lot more robust. I think that way you have like better control, better measurements on the models. Binary classification is very well understood. Multi-class classification is well understood, but like under the hood in scikit, for example, it's actually usually just an array of binary classifiers. Anyways, so it simplifies many things in my view, but your mileage may vary. In any event, so here we have this partial info thing happening where you only get 1 piece of the reward signal and you can only update 1 piece of your vector of models per trial. So here we do that. We update the cumulative rewards, we update the models, and then this does some logging. That's a single path or epoch. This loop just wraps that. It runs it over epochs and then returns which is the percent outperformance of the RL policy, right? And it's going to do this for various values. This guy, dynamic percent is not a great word, but what this is really is, where is this defined? Right here. A vector of values, all of which are spaced out by 0.1, so like 0, 0.1, 0.2, 0.3, etc., which represents the fraction of trials in which the win probabilities are scrambled. So if the win probabilities are never scrambled, then you have a fully stationary environment. They remain the same, and so greedy decisions are likely to perform well. Because, well, I'm not going to like give you the whole answer just yet. But it's unrealistic to imagine that the environment is so non-stationary that like the win probabilities are being scrambled 100% of the time, or even 80 or 70. It's very high. But that's what this is doing, just to test out like how does the thing hold up. So this takes about a minute to run. Because it's on GitHub, it just takes like the results of the last run. These are the outputs of those various logging statements, blah, blah, blah. What you get is a picture that looks like this, which is very elegant and reassuring looking. It's interesting to compare how this looks for different values of that XP, and I'll show you that in a minute. On the horizontal axis, again, you have these 0.1 spaced values that corresponds to the percent of trials with shocks. How many times, what percentage of the time does the win probability vector get scrambled, right? Why is that important? Again, that's a non-stationary environment. That means that any kind of decision rule that is learned is now non-optimal in general, if that win probability vector gets scrambled. And then the percent outperformance of the reinforcement learning policy is on the vertical axis. So you can see something that I think looks pretty intuitive. Generally, reinforcement learning works. That's good news. At least in the sort of like miniature version that we've exhibited here. The far left and the far right, if you like, in this plot, are the perfectly stationary and perfectly non-stationary environments. In a perfectly stationary environment down here, with zero value, there's no way to ever make up the cost of exploration. Remember, you're basically buying information. The stuff about local optima, et cetera, like averages out over epochs. That's why you do epochs. But if there's no opportunity to adapt to a changing environment, there's no opportunity to gain new information and exploit it, there's really no way to recoup the cost of exploration, and so you get a negative lift. You get underperformance versus the strictly greedy paths. Just doing the easy thing every time, if it's always perfectly predictable, makes a lot of sense.
That's what the vertical axis is compared to a fully greedy
Yes,
version. Okay.
exactly. It says percent RL outperformance. That's like the outperformance versus the greedy baseline.
Okay.
It's really the cumulative rewards of one versus the other minus one divided by the other. So it's truly the percent outperformance. So here, when it's fully predictable, the environment, it's negative because, again, if nothing is changing, then greedy decisions are dominant. Yeah. When there's a lot of signal in the environment, but there are some changes, like for, let's say, the slightly non-stationary region, like up to, say, 0.7, I would say, even 0.6, 0.5. RL does quite well. And its effectiveness decreases over time as there's less and less signal available in the data. Again, that's pretty intuitive. Down to the limit, really, where 100% or 90% of these scrambled trials, there's not much signal to grab onto, so it's not going to do very well compared to the dominant strategy in that situation. If things are really constantly changing, is you only use a uniform vector of probabilities because you never know. Yeah, so it's difficult to beat just in a 3-arm bandit problem, 1/3, 1/3. Yes, sir.
Sorry, I think I missed something earlier. What is the RL in this case, the epsilon greedy?
No, so there's no epsilon greedy exploration taking place here. Alternatively, the exploration strategy is to use the full rewards distribution and sample from that in order to make a forecast of the expected reward. As opposed to just taking, it's right here, as opposed to just taking the
Catch its exploration.
Sorry?
I didn't catch its exploration in the code, sorry.
Yeah, so it is right here. It is right here. The beta distribution has its maximum at this value, alpha over alpha plus beta, right? It's a 2-parameter distribution. So the greedy version is only representing the information that accumulates through the expected value of that distribution, right? That is consistent with exploits only decisions. It's only using this first moments of information. Alternatively, down here, this is where the exploration enters the picture because it's taking a random draw from the full distribution. Instead of just hitting it with an expectation, it's sampling from that distribution. So you have a much wider range of potential outcomes. It's not as coarse or as manual, I suppose, as the epsilon greedy, where in that case, you like flip another coin and say, okay, if it's below some value, then I explore versus exploit. In this case, it's kind of like a little bit more baked in because it's using this Thompson sampling strategy. That's a good question because that's like the main difference between these two. Does that make sense? That's why there's two classes here, because this estimated win probability has different expressions on the right-hand side of the in order to capture exactly this, the greedy versus the RL.
I think I was just confused because the greedy is a reinforcement. It's just like the greedy reinforcement, like strictly
Well,
greedy.
I think strictly speaking, you could say that the greedy version is a beta binomial model that is not using reinforcement learning because it's not doing any exploring. But that's, again, getting pretty specific about the vocabulary.
Okay.
Does that make sense? I mean, these are important points, and I'm kind of compressing this into like as little area as possible. So then you get a picture that looks like this. And interestingly, so I did this and I thought that looks good. If you start messing with the win probabilities, like a lot depends on the assumption that you make, which are the true win probabilities. If you start messing with the win probabilities, you see that this nice picture starts to loosen up. When the maximum win probability is 0.9, there's a really dominant arm, right? It's really important to choose the right arm. And in that case, especially in like the 0.1, this bar right here, the slightly non-stationary environment, you can get, according to this thing, up to like a 9% outperformance in that simulation. You can see this go down over time. Like here, when max P is 0.7, that goes to 6%. Here it goes to even lower. So you can see that thing loosening up as a function of that particular parameter, as well as how it behaves across these different levels of stationarity or non-stationarity in the environments in the horizontal axis. And then the vertical axis, again, is the difference between the greedy versus non-greedy strategy. So again, this is like maybe the simplest way to, my goal was to like technically demonstrate reinforcement learning in the fewest lines of code. I think that this is basically how you do it. And it also exhibits a toy example of what the offline optimization, like simulation environment would look like. In a real application, synthetic data is really important. I really like using synthetic data. Like if you're familiar with the scikit API, there's these functions like make classification and make regression. Really great, not just for Bayesian models, but anytime you want to learn about the behavior of a model or what your like empirically trained model outputs might be telling you, synthetic data definitely underrated. In a real situation, you might have this offline optimization framework set up using synthetic data to learn about like which one of these models performs better under synthetic conditions, or again, using historical data sets. The way that works, now this is another tricky bit. The way it works though is that you can do this with any supervised data set. You have to start, again, it's kind of inside out. You have to start with a baseline policy. Instead of starting with the data set, start with a decision rule. And that decision rule could be just like uniform decisions at every point. But you have to generate a stream of actions, a path of actions from a baseline policy. That corresponds to the path through the empirical data that your auditioning bandit, candidate bandit is permitted to take, right? So you have like the logged policy, now you have your candidate policy. At trial 0 or trial K, your candidate policy makes a decision. If it is the same decision, literally, if it's the same action that the logged policy has taken, that record goes in the sample. If not, that record is discarded because you can't make the counterfactual assumption that this is no bias and that this is simulating an online. You're violating some like causality thing there. This is like the John Langford. I think it's pretty amazing. Move. It's really just like a mini sampling trick that unlocks this huge family of powerful techniques. This is why, again, you have to go through many epochs because you're doing sampling at every step. So, if you have like your baseline policy is say uniform, you have 5 arms maybe, and 1 million records, you go through the first time at least, you expect to keep only 20% of those records. So this is why many paths are required to get results that converge. Anyway, this is what offline optimization starts to look like. And then you can do fancier things like the reward shaping, embroidering more information in the target variable. And that's where you train up the supervised model, feature selection, deep, shallow, gradient boosting, all that jazz that you're familiar with, or something dead simple like Thompson sampling here. excluding the feature set that are just doing the 1D. So I've said a lot about a lot of stuff very quickly and intensely, I think. I think I'll stop there. Any questions?
How do we pick a slot machine? You didn't get to that.
How do you, sorry, say it again.
How do you pick a slot machine?
How do you pick a slot machine? Well, it's like, it's a stretch to say it's like picking a stock. In the short term, like in a single trial, it's all noise. Over a sequence of trials, there are strategies to do it. And what it amounts to really is what kind of data can you get? And what does your reward signal look like? And what sorts of, the way that I typically have done this is like you read a bunch of papers. They say, we tried this for Explorer, we tried that for Explorer. This worked well, this worked well. You try stuff out, and there's like textbook examples you can use too. Epsilon greedy, the decaying epsilon, where epsilon gets smaller over time, pretty intuitive. Something like softmax, where it converts your vector of probabilities into something a bit smoother, and you can sample against that. There's all kinds of things you can try out. That's just on the explore side. Then in addition, you have exploit. That's again just amounts to like what features go in my model, how complex is my model, what do I think about precision and recall, all this kind of stuff. You get something to look good offline, you test it online. That's basically how you choose which one to pick.
Is the premise similar to your example in that a machine has an embedded like win probability, but every once in a while they get scrambled?
Yeah,
That's how slot machines work?
I don't know. If,
I don't know. I honestly have no idea.
I don't know. I don't know the answer to that, but the particular application where I've done this is in e-commerce, right? So suppose, for example, for a catalog of SKUs, bunch of items, instead of a single price, there's 5 prices. And dynamically, you can figure out how to allocate traffic for a given SKU across those prices based on what you observe from things like a binary reward signal. You can include features or not. And the external shocks come from interesting. I mean, it's such an e-commerce is cool because everything is so like concrete. If everybody is out of stock in paper towels except for me, I might observe that the clearing price for paper towels goes up if I let it. Whereas if I just kept my price where like the merchandiser says this is how much paper towels cost, you don't capture that additional demand. If you're doing some exploring, you can follow the market up and start charging more for paper towels as they go out of stock elsewhere. Or you can understand how, if your competitor introduces, some kind of new product, you can look at the difference between like first party and third party products, but basically do a spot where if your customer all of a sudden decides that they really dislike buying something from you or from them or from whatever, you capture these changes in the environment. If there's a promotion, whether it's on somebody else's website or on your website, just any kind of external shock, something exogenous to the model. Having some kind of explore strategy makes you robust to that because you're always going to be looking around to try to figure out how do I not get hosed by something slightly changing where the greedy decisions like never see those. That's kind of the gist. Does that make sense? Yeah.
I want to understand this graph more. I think it's very interesting. So on the right, basically pure chance, not going to ever find a pattern or algorithm. When there is opportunity for one on the left, there is optimal algorithm, and no amount of exploration is going to ever outperform this optimal algorithm. Why is 0.1? Why is that so much more beneficial to use the reinforcement learning and 0.1% trials with any shocks? And what would it look like if it was like 0.01? And why does the max P change the chart so much? It's 9.9 here. Why does that change the?
It's kind of interesting, right? I mean, you see a picture like this, and you're like, this has got to has that shape. It's got to be telling you something. So the reason that, regardless of the value of max P, these are orthogonal. Regardless of that value, when the thing works, like you can see here, basically it becomes detached. Like it's not exactly working. You can see for lower values of that max P, you just get noise. So it has to have, that has to be sufficiently high, let's say. In the sufficiently high regime, you have this maximum at 0.1. That's where non-stationarity is present, but only to a very light degree, so that the environment is very predictable, right? 10% of trials in that case are the ones where the win probabilities get scrambled. So in the other 90% of trials, it's pretty predictable, but those flips happen. And when they happen, the reinforcement learning algorithm can adapt to them, whereas the greedy one can't. And that's where it really outperforms. When the flips are happening so much, like there's more flips than non-flips, then there's really nothing for the model to grab onto, and it starts to, like down here at the right side of the graph, on the right-hand side of say like 0.5 inclusive, you're getting more noise than signal basically from the environment, and so the decision engine isn't really grabbing on it. That's why you observe this decay. At least this is how I'm explaining it to this. Why now? Then again, there's this orthogonal dimension of that max p number. Down here, this also depends on the other values of p, just the maximum, but that's kind of how I started to see it. If the expected reward across arms is really low, then the gains from being better at selecting the right arm are correspondingly lower, right? If there was one arm that produced like a reward of 1 million and the other ones produced rewards of 0, then that would probably be like really, really, really high. I mean, I'm not sure the thing would work, but basically it's sort of like if the expected reward conditional on being right is very high, then the benefits of reinforcement learning are correspondingly higher. That's what this thing is demonstrating. Running it across, like, you have all these nested loops, steps, paths, values of this thing, different values of p. This is all basically to slice and dice and like kind of kick the thing until you can get a story out of it and show a picture. As you know, that's what the data product really wants to, even for a little simulation of this. Really good question. Any other questions? Yes, sir.
I think you started talking about it, but I didn't quite wrap my head around it. When you're building your simulated environment for offline use, what is a realistic strategy for introducing these shocks, this non-stationarity? Because I feel like that is just, the possibilities are endless for what that could be. And in my mind, I was thinking, well, you could sort of, as you progress through the epoch, you progress through your data set in time or something, in terms of your sampling strategy. Is that something viable, or is there like a standard way to do this?
Yeah, that's exactly right. So the epoch basically amounts to a trip through the data set from like time 0 to time 15. Those simulated shocks, I think in general would not be present in a real kind of application. That's just to illustrate for our purposes how and why this thing does better when there are some unpredictable elements in the environment. In the true setting, like when you're using empirical data in finance, it's really common called backtesting. When you're using empirical data to basically backtest, then those environmental shocks are imprinted and present in the empirical signal. Yeah. So in this case, because it's just like a little simulator, that's why I included those shocks to get this picture. But when you're using an empirical data set, you wouldn't have to do that because again, like those random shocks and stuff, like this guy went out of stock, on that date, that shows up in the data. I mean, those are the signals that you're trying to grab onto.
And I guess I'm thinking about the shocks and the non-stationarity that has never been observed. Like, is there a clean mechanism to, I'm just imagining this talk taking place in December of 2019.
Yeah.
Right. And how you have all sorts of typical, depending on your application, maybe it's typical business cycles that you're observing those various shocks. But how do you incorporate all those what if scenarios? What if there's a pandemic in 3 months?
Yeah.
What if there's a major technological disruption? Whatever it is, like is there a clean mechanism to do that?
I'm not sure that I can vouch for its cleanliness, but again, to use the financial analogy, this is basically like scenario testing. And you would generate like a synthetic data set over a future time horizon where you say like some event is taking place, and that's contributed to these features or data or whatever signal, high dimensional process following a distribution that's slightly different in ways that either you specify explicitly and have like a generative model, like a Bayesian model, and you say that the parameters went from here to here, or alternatively they differ in some other like non-parametric way, and you say, okay, I'm gonna generate that another way. But basically you would then be running the simulation against synthetic data that's generated, yeah, under those assumptions of like this scenario having taken place. Again, it's like a counterfactual kind of, yeah. Interesting question. Any other questions?
Just expressing appreciation for students.
Oh, yeah, the Zoom, thankfully the AV gods have been good to us today. So.
I would bet that with the slot machines, that there's some method of networking the machines together to detect if there's, you know, people
Whatever
are,
they do, it's making money from that.
yeah,
I don't know how it works.
right,
seems
because
like
if
a great
the
idea.
machines we're talking to, they sort of sense this like behavior of like, so
Yeah,
zooming in on one or something like that, they could just sort of shift,
Yeah.
switch the probabilities.
my knowledge of slot machines is extremely limited. I mean, that was it. But like, I've heard of people thinking that like, oh, this machine is hot or whatever. Maybe that's
Yeah.
it's like the hot hand thing. Just an artifact. I really.
I think I heard about one story where someone actually got access to the actual algorithm that some machines used, and then they gamed that pretty successfully. But
Are their knees broken now?
I don't know.
I think those algorithms are pretty complicated because it's not just trying to minimize the amount of wins that people have, but you want to give people enough wins that
Right.
they want to keep playing.
The dopamine thing.
Yeah.
It's actually pretty interesting. Any other questions? At all? Yeah, please.
So when you, in the beginning, you asked how many of you have, used reinforcement learning algorithms. And I didn't raise my hand, then hearing you describe it so eloquently, I was like, wait a minute, I feel like I've done this a lot, and I just didn't have a language to describe this. In my mind, I'm kind of struggling with trying to understand the difference between this. Obviously, there's some technical differences, but the difference between this and like any optimization algorithm, like a genetic algorithm,
Yeah,
ant colony algorithm, like anything that's probing some opaque thing.
Yeah.
And has an objective function that they're trying to maximize.
right.
Like in this example, it seems like this could just be it's an optimization problem for an objective function that has 3 parameters that are discrete.
Yeah.
Maybe it's just on or off in this case. And like I'm trying to understand like what's the difference between this and just optimization in general? Is there a difference?
Yeah, totally. That's so interesting. It's like, I remember being surprised when I learned that I've been doing machine learning all along. I was just calling it regression. It's like, oh, but I think that it's true. Like, this is a really generic, again, it's not an algorithm. It's a little bit more like cross-validation than an algorithm. It's a framework, and you can apply it basically to any kind of optimization problem. If you can define it in terms of a reward signal and a sequence of repeated trials. This is why they can use it to like play board games or play video games or drive cars or build cars or train language models. It's capable of doing like all these different things. The original theoretical examples, maybe the oldest one, I'm probably wrong, but one of the very oldest ones is a 2-dimensional, it's called the cart push cart problem. Cart box push cart, something like that. Basically, your inputs, you have a cart with wheels and a vertical like stick on a hinge.
Oh, you're balanced.
Yeah, you're balancing it. So basically by looking at the angle that the thing makes, again, this is all like in a stochastic simulated environment, you decide whether to move the thing left or right. And the goal is to just like balance it for as many trials as possible. So then the difficulty, I mean, it's like, again, solving any kind of, you guys are all data scientists, solving any kind of data problem. If you can transform the problem into a framework that can be addressed with a data solution, if you can define a target, define a feature, and define an approach, then you're kind of like most of the way there. Building models, I always tell people building models is like easy. But if you can do all the rest of that stuff, scikit will sort of do the rest for you. But yeah, you're probably right. This shows up like, I don't know, the opportunities. It's not, I know language models are like very influential and pretty trendy right now, but reinforcement learning is not going. It's like really dramatically powerful. Not to ding language models. They are what they are. Yeah.
So I'm not sure, Ezra Klein, he's been my favorite journalist I've been following lately. He's really written. It's open AI to confront journalism world. And I think last week or 2 weeks ago, I heard a podcast on the Brian show. Why adults lose the beginners. And
Oh, yeah.
yeah, and so they talk about exploratory versus exploitation.
Oh, interesting.
Learning styles and how really obvious it is in children versus adults, and how children have this incredible ability to learn very rapidly, very quickly, high plasticity in their brains versus adults, which are who are primarily trying to exploit and get as much out of what they know and understand about the world.
Yeah.
And I don't know, I thought they did a great job, really kind of hammering down this explore versus exploit.
That's so interesting.
So interesting. That just, I didn't central.
A lot of people, maybe even the origin of the field was and is in cognitive science, like trying to understand trying to model learning. Like how do humans, how do babies, how do animals learn? That's where a lot of reinforcement learning theory came from. And these computational applications are like downstream. Like I have a friend who's in cognitive science, he does a lot of this RL stuff, but it doesn't look like this. It's like how can we use this language to understand what's going on in someone's brain? And ideas like explore and exploit are like, again, so generic and so powerful and so widely applicable. I think that it's compelling.
Can you talk a little bit more about your career path? And is this
Yeah.
what you do in your current job? Have you used this in other?
Oh, such an interesting question. Yeah, my currently between engagements. I was doing a lot of this at my previous employer. I've done a lot of this sort of thing again in e-commerce. They have an interesting story, which I'll save for later. But my own background, like math, physics, economics, finance. So I'm from San Diego. I moved to New York City to go to graduate school. I started working in the financial markets, and then I was like, Wall Street's not really going to do it for me. I'm going to be a physics professor, and then data science was like the average between these two. I was in New York for 15 years, and we moved to a couple of years ago, and so now I'm doing stuff like this. Makes me break.
Can you name names?
Name names.
E-commerce-wise?
Yeah, so I used to work at a company called Boxed. I'll give you the full scoop. They were an e-commerce online retailer. Went public via SPAC a couple of years ago, which is a very aggressive move. It's increasing interest rates did not play in their favor. Now they're in Chapter 11, and most people have been laid off. However, they are the owners, the creditors who now own the assets, have turned off the e-commerce business, and they're moving forward with price optimization via reinforcement. So they placed all the chips. So it just might work. Good luck to them.
I don't know if this is good or bad, but I'm the marketing director for one of the original investors in Box.
Oh, wow.
Yeah.
Close.
Yeah.
Which company is that?
Social Starts.
Well, I don't know. Social Starts.
We're very excited for Che.
Yeah.
Originally.
He's a great guy.
He's a great guy.
He is. What else can I tell you? I've been talking.
Are you most interested in astrophysics?
Oh man. Astrophysics. Okay. My field was pretty pencil and paper physics, theoretical stuff. I was working on something called this is a mouthful, the ADS-CFT correspondence. This is to do with like holography and the duality between spaces of different dimensions that can exist, and how basically if you can solve a theory in like one environment, it actually translates in some way to another environment. There's like black hole implications and stuff baked in there. It's quite a long story. Not all of that directly useful or interesting. My wife is a therapist, and so I used to talk to her about this stuff, and she would stop believing me like halfway through the first sentence. 26 dimensions that are.
I gotta ask, so if you had to put your money on it, do you think we're in a simulation right now?
That's difficult. I would guess probably not, but I think it's safe to say because it's unknowable by definition.
Probably driven by a reinforcement.
Probably by some kind of agents, brain in a jar. Yeah, so physics, I mean, I don't do a lot of theoretical physics these days, but I'm a big evangelist for that kind of thing because you learn how to learn, and that's sort of my litmus test for when I'm hiring data scientists, for example, or like trying to talk to people about how to do data science. Maybe your opinion is different, but if you can figure stuff out and you're curious, I think you're pretty golden. What else?
Are we over time? Doesn't feel like it at all. It's great. It was great. Yeah. Thanks a lot, Jason.
Thank you.
So
Pleasure.
one thing is I want to apologize to everybody that was messaging and texting me about the front door. And I realized I could just sit here and open the damn door with a button on my phone. So in the future, I will just include my phone number and you can text and we'll just figure that out. It'll be like, it'll be a little bit clunky or whatever, but I'll just sort of like open the door a few times and then you go through and you have to get through the second door a few times. But I think that's probably the best way to do it. Just every 5 minutes or so, I'll just open the door.
The other
But
solution
also
that,
people at 5:30, a lot of people seem to be able to get in when other people go out, right? I mean, what was the longest that anybody waited?
I think I waited 2 minutes.
2 minutes? Okay, but it's still not nice to have that sinking feeling, right? Like, get here. Okay. You're an optimist.
I'm an optimist.
Okay.
I have the exploratory mind.
Yeah.
It's a great room.
Yeah, it's nice. And the sun behaved. It was like, it
Yeah.
only got bad right at the end.
Yeah, that's
so-
right.
Right, it's a good view.
Yeah, it's a good view.
It's a nice spot to work in.
Yeah. Yeah, I like it. My office has no, they have views when I walk around. Have people like Jason here, like hang out.
And in the wintertime, it's still nice.
Oh, yeah. They heat it. Yeah, no.
Like England, we have heat is optional.
Yeah, it's nice. And if any of you like it, I mean, I think you can come, they have all these things, you can come your first time and it's like free for half a day or something like that.
Yeah.
And you can like, I think you can come with a friend or something for on Fridays, things like this, all sorts of deals and things. So just ask at the front desk and tonight, you can just come if you have something you want to just work on your laptop. It's a nice place to hang out.
is the bar open for people that want to stick around or not?
I don't think it is. Yeah, the bar thing, I think that the happy hours were, one of the issues that Hula has had is that they rented out some really large office spaces. Early on, they were psyched to have leases on everything. Of course, all the stuff going on in 2021 or 2020. So they leased all these offices, and then some of the very large offices that have companies with lots of employees, not very many people come in. And so they don't have, everything is leased and that's great, but they don't have foot traffic. And so that affects things like the restaurant and the bar really, being able to sustain themselves. And so there was, the intention was to have like a regular happy hour on Wednesday, I believe Wednesdays or Thursdays. So we were trying to kind of like match with that so that, we could all be here to meet up and then go out and there'd be a lot of people around in the bar. But I think that there just hasn't been as popular as they needed it to be. And so they're not doing the happy hour as much. So, could do pizza or something. We should get back into the whole pizza thing. But the other thing is that I think I didn't get to the end of my slideshow where the point where I shamelessly beg for money. The bathrooms, by the way, are down behind the front desk. If anybody needs that on the way out, behind there's a bamboo wall. You go in there. And then parking, if anybody parked in the parking lot, technically you're supposed to pay. I think, and I don't know if anyone's ever gotten a ticket. No one ever reads the instructions, so. I don't know, but I've never heard of anyone getting a ticket, but you might. And then, yeah, we need to, so we have to pay now for space. Before we didn't have to pay. Now we have to pay for the space. It's like, it works out to be with tax and fees and things like $140 each time we rent the space. And so we get, some money from Posit that covers a lot of what we do, but we definitely need to like collect cash donations and Venmo and things like that at the meetup. So, whatever you feel like donating, I can put open Venmo on my phone. Polly loves to take cash. She's the treasurer. So she says she counts it, carefully. So. Anyway, yeah, and then we can certainly just go, we can stay up here or, head downstairs, there's couches and things or whatever. Everybody's welcome to hang out.
That was great. Thanks for speaking.
Thank you for having me.
And your code, can you post the link to GitHub?
Yeah,
Yeah, and then, and so I'm gonna go back and watch so I recorded this and definitely, I think. Yeah, it was a dense talk in some places, and so we're putting everything up on YouTube now as well. Where's the recording? Top left.